Okay, great. Well, thanks very much for including me here. It's really wonderful to be part of this conference. I'm going to tell you about some of the things we're doing with wearables. I like to show this slide because it frames at least the problem as we like to think about it. That is, we like to think, as a scientist, I like to think about health as a state where hopefully most of the time you're healthy, but on occasion you may get ill, sometimes very severely. And really what we want to do is understand the factors that contribute to this and ideally keep people in a healthy state. So obviously many things do contribute to this. Let's see here. Great. It's your DNA and then all these other various things, many of which you can track with various wearables and other sorts of measures, some of which we've heard about already. One area that I would argue that we're quite deficient in, that we've spent a lot of time on, maybe next meeting I'll talk about this, but this is capturing environmental exposures, which I think is pretty powerful. So I would argue there's been a revolution in several different areas that make measurements either directly or indirectly of these various things quite possible now. One is the genome sequencing revolution we're all familiar with, so you can all get your genome sequence. Just out of curiosity, how many of you had your genome or exome sequence here? Wow, what an enlightened crowd. That's amazing. Quite good. All right. Then the other thing that brings everyone here are those wearables. I think we'll hear a lot about this. But I would argue, which doesn't get quite as much attention, is there's been a revolution in mass spectrometry, so you can now measure tens of thousands of molecules in bodily fluids, as well as actually in environmental situations. So we can really capture a lot of information a lot of different ways. So many of you may know that a number of years ago, I guess it's been about 7.5 now, we set up something we call personal omics profiling, where basically in addition to taking standard medical tests, measurements, we've been making lots of other omics measurements. So your genome and then all these other ohms that are listed up here, we've been measuring our people, and we've been doing this longitudinally. And you don't have to take pictures. We can figure out how to share slides, I assume, through this thing. But anyway, we make basically 14 different ohms of measurements on people as we follow them over time. And then more recently, about 4 years ago, we started adding on the biosensors, and that's what I'll tell you about today. But generally, the scheme is as shown here. We sample people roughly every 3 months or so when they're healthy, and then when something evil happens, like a viral infection or other sorts of things, bike accidents, we take many more samples. In my case, we've been sampling me for 7.5 years. I've had 10 viral infections, Lyme disease you'll hear about in a few minutes. Also had a bike accident, woke up in a hospital. I don't look for these things, but if something evil happens, you might as well get good data out of it. All right. So anyway, one reason we're doing all this is we're really trying to, there's a lot of words, I'll just summarize. We're really trying to define people's baseline healthy states, trying to understand what it means to be healthy, how does that differ amongst people, and then how do we change differently when we react to certain things like viral infections, dietary changes, things like this. Along the way, we discover lots of important things that do influence people's health, and I would say actually we've caught 2 people with early stage of cancer as we've been profiling people, things like that. So we really have learned quite a bit from the study, both that affects their health as well as research. So right now we're studying about 100 people, so we've enrolled something like 115 starting about 5 years ago. We've been following roughly 100 people for about 4 years now. And the sampling is pretty much what I said. We sample them every 3 months when they're healthy, and then if viral infection or various stress responses, we have people doing colonoscopies, for example, we'll take many more samples during that time. And a variety of our folks have been doing dietary studies, so we've been collecting a lot of information about what diet does on a personal level to their biochemical changes, their microbiome, things like that. So one important part of all this is that our participants, not all, but nearly all, have agreed to make their data completely open access. So as we've been sampling, we now have roughly 1,800 plus samples. Over time, the first 1,000 have been analyzed on folks, and all that data is at NIH, and I think it's up there, but if it's not, it will be up very soon. It's at the data center, so all of you can access it, including genome sequences and such. So basically, people, again, have agreed to make their data open. And what's nice, this slide's a bit dated. Most of it shifted somewhat more to the right, but we have quite a few people at multiple samplings over many years, so you can actually get quite a bit of very useful data with all this deep omics profiling associated with it. All right, I'm not going to go through all the venues. I'm just trying to set a little background for the wearables part. But one thing that was kind of interesting is we sequenced everybody's genome and poured over it in incredible detail. I don't know for those of you who've had your genome or exome done. There is useful information. One thing that's come up quite a bit is how often is a genome sequence useful to people in a medically actionable situation. So it was useful for me, many of you may know, helped me catch my diabetes early on. But we went through other 70 folks in incredible detail, and 12 of them actually have information that affects their medical care. That is to say, they have a strong penetrant, at some level penetrant mutation that can put them at risk for these various diseases. And so these are the list. Two means there are two individuals here. But one example that many of you may be familiar with, one of our individuals has a BRCA mutation. It's a male, but it does put him at high risk for breast cancer, and learned last night, prostate cancer. So he actually will and does get screened for this now as a consequence of this. And the same is true for all these others. In one case, this is a case where actually this individual, we saw this along with his father had a heart attack the same time we were sequencing his genome. And it turns out we think we found this cause of the mutation. It turns out he actually has a heart problem he was not aware of that basically got revealed from his genome sequence. And now he's on drugs as a consequence. And this person actually was, we do have one or two, I forgot to say about 60% of our folks are pre-diabetic. A few of them are diabetic. This was a person classified as type 2. Turns out he's actually something called a MODY mutant, which is very different. And the way you treat a MODY person is 100% different than the way you treat a type 2 diabetic, actually. In fact, there's a famous story out there of someone who was getting insulin for their entire life. They were classified as type 1. It turns out they were a MODY person. Had they caught that early, he would have been on a different treatment, and he would have saved 21,000 insulin injections over his lifetime. So we would argue, yes, it doesn't give you valuable information every time, but if you're one of these 12 people, it's a big deal. So that's why we think genome sequencing is powerful. That's my plug for that. So on the wearables. So there's lots of other very fun stories associated with that, but it's a wearables conference, so that's what I'm going to tell you about. All right. So about 4 years ago, we realized the power of this, that collecting continuous measures should be very useful to supplement whatever we're doing with the omics profiling. And so we started looking at lots of different devices. There were about 500 out there at the time. So we sampled about 30 of these. We ultimately settled on two that all of our participants have. One was a basis watch, because they actually at the time could get us the information we needed. That was a big deal. And then I guess the other was a Moves app that's on there. So we can measure all their steps and have an independent assessment. And then for me, actually, I wear 8 of these devices, well now 9, pretty much every day. I have 3 smartwatches here. You may wonder why that's valuable. Well, it turns out the basis watch is one example. That actually got pulled from the market. It overheated in a small fraction of people. And so that went away. We liked it because it had a lot of measures that we were interested in. that others didn't have, and they were easy to work with, so that was useful too. So we think having redundancy does have value for those reasons, and others, it turns out, as well. All right, so anyway, let's see, here's my Aura ring too that you heard about earlier. So these devices will measure lots and lots of different things. So you've heard about some of this already, heart rate, skin temperature. Turns out all of these are valuable in different contexts. Something called galvanic stress response. It's really a conductance across your skin and so on. Here's pulse ox and so on and so forth. Even radiation, which we discovered Scripps is about 2-fold higher than other backgrounds. So it was a hotel I was at last night. So some of these things are a little bit elevated. Most of that's still in background levels, but you will occasionally, there was one case, probably shouldn't get into this too much, but there was one case where the thing just buzzed out of control. It turns out that was when I was at City of Hope giving a talk. It was in a small cafe, and presumably it was somebody there getting radiation therapy or something like that, because I went back to the cafe twice later, it was down the background. I didn't dare ask who's getting monitored here, but it was really 800-fold higher. And of course, it's higher on airplanes. That's only 15-fold. Anyway, sorry, I'm digressing from what I wanted to tell you about here. Anyway, you can make lots of different measurements. I forgot to say it's slightly elevated in this auditorium, too. I checked earlier. All right. So why are we doing all this? Well, it's really to see what kinds of, the power of what we're doing both for omics and this, is we're trying to get an understanding of people's baseline levels and then look for deviations from the baseline. That's really what this is all about. And so what we're doing is establishing personal baselines for folks. This is my baseline from several months of data. Basically, this is, first part I'm going to tell you is things that are so obvious you would expect, but then you'll see how you use this to find things that perhaps are less obvious. So this is my sleep patterns. This is a 24-hour cycle. So I sleep at night, wake during the day, occasional nap, back to sleep at night. Okay. Heart rate, same thing, low at night, high during the day, goes back down at night. Skin temperature, this is different from core temperature. Skin temperature is high at night, drops during the day, comes back up at night. So these are the various baseline measurements you can make, same for pulse ox that has certain patterns, circadian patterns as well. That was me. This is 43 other people. I won't go into this in detail, but we all have different baseline heart rates, skin temperature, blood oxygen, so on and so forth. We all have different baselines, and that pattern will generally be similar during the day, although there are some unique features. Here's one example. This is activity patterns of our participants. You can roughly group them either systematically using various clustering algorithms or even visually it becomes pretty obvious. You can group people into 4 different patterns. These are folks who are basically active somewhat continuously during the day, so not active at night, continuously during the day, back inactive at night. These are morning people. They spike in the morning, presumably exercise. These are morning and afternoon people. 2 humps, these are 3 humps, morning, afternoon, evening. So you can group people into different basic patterns, okay? So these are some of the things that you can see. So then once you understand people's personal baselines, so the question is, when do you see deviations from that baseline? Well, here's one of the first things that popped up. This is popped up on me. I travel a lot. It turns out, this is known already, that your blood oxygen, your pulse oxygen does drop on airline flights. And the reason for that is the cabin's not as well pressurized roughly to 8,000 feet. Discovered more recently, we just published this in the beginning of the year. Turns out there's a barometer you can get on your iPhone, which is quite accurate actually. There's several apps for that. So now I know exactly what the air pressure is in an airplane when we measure this, but we didn't have time. But anyway, this is an example. So this is a short flight, I think San Francisco to San Diego, as I recall. That's altitude in green. This is my pulse oxygen, so it starts high, plane goes up, your pulse oxygen goes down. They stabilize the pressure at a certain level. There's my pulse ox there, comes back when the flight lands. What's not so well documented in the literature is just how much is it down and for how long. Turns out this is now an underestimate, we know. Turns out for pretty much all the flights that are a certain high, your blood oxygen, for me, it's usually around 94, but can go lower. This part's accurate. 5% of the time, it'll be 90 or less, which is kind of low, actually. And most of the time, it's in this range, 96 or below. And that 96 number is important for something I'll tell you in a minute. This isn't just true for me, it's true for everybody. There are no exceptions from our cohort so far. These are the first 18, but we've measured this on many more people now. Green is, excuse me, on the ground. Blue is in flight, so this person here, that's what their average, their blood oxygen is on the airplane, that's on the ground, so on and so forth. Everybody's blood oxygen will drop on a flight, no exception. All ethnic groups represented here, okay? So then, that's nice, you get these patterns. So why is this relevant? Well, it turns out, couldn't find this in the literature either, which is, it turns out we think drops in blood oxygen correlate with fatigue. So the bottom line here is for me, you can do a random test where you ask whether you're alert or tired and then look at your blood oxygen and score it that way. That's shown up here. You can also do reaction time tests, that's here. But basically for me, if blue is tired, red is alert, and if 96 or below, I'm generally tired. 96 or above, so 96 threshold, I'm alert. And here it is on the ground, here's in the plane. Numbers pretty similar, 96 is my threshold. There's reaction time versus blood oxygen, so you get slower reaction as your blood oxygen drops. So bottom line is we think that the reason you get tired on airplanes is because your blood oxygen is low, because the cabin pressure is reduced. So again, that's probably pretty obvious, but it's not so obvious out there. Many of you probably thought that you're getting tired because you've been working too hard. That may be true too, or maybe partying too hard, I'm not sure. But the point is that we think you're tired not for those reasons. You could be, but we think you're tired because the cabin pressure is low. So for those of you who are workaholics like me, that's extremely disappointing news. But it turns out there's some saving grace here. For very long airline flights, it turns out you can adapt. And for me, that magic number is 7 hours. So if the flight's 7 hours or longer, my blood oxygen starts coming back up. So here's from Frankfurt to San Francisco. Starts there, drops. It'll drop even lower when you take a nap, which you can measure with your devices. But it always comes back up. And this is a summary of many flights. You can actually see this. For me, it seems pretty consistent. I don't know if that's true for others, but so anyway, at least from these longer flights, if you're starting out not so efficient, there's hope for you towards the end of the flight. All right.
Better in business class?
Better in business? No, we've measured that. It's exactly the same. So I've been in all kinds of seats. Doesn't matter whether you're near the exit row or the other. We've summarized all these things. It's also very interesting. Dreamliners are not. You'll be dreaming on Dreamliners. Yes. Okay. So this is all nice because it does give you some background information. And then again, how to use this. Well, this is one example in which it turned out to be incredibly useful for me. So it turns out I'll give you a little backstory. This helped me figure out I had Lyme disease. The backstory behind this is I was helping my brother put up fences in rural Massachusetts where 55% of ticks are Lyme infested. And then 2 weeks later, I was flying to Norway via Frankfurt to be able to go on vacation with my family. So it turns out on that second flight from Frankfurt to Oslo, which is a short flight, on most short flights, my blood oxygen behaves like this one in green. This is a summary of many flights. But on this particular flight, my blood oxygen dropped. The median was 90. Okay, when I landed, it didn't return to normal. It stayed around 90, whatever that is, 95, which is pretty low for a short flight like that. So that tipped me off that something wasn't quite right. I also looked at my heart rate, and it turns out that was elevated, and then I later learned by looking at my monitors that my skin temperature was elevated too. So this is 2 years of data. We'll drill in a little more efficiently. This is 2 standard deviations. You can do this by mean outliers or increased median measurements, but outliers turns out to be a little more sensitive. Anyway, it turns out my heart rate was elevated upon landing as well. So I knew something wasn't right because I measure myself all the time, and I knew this was not normal. And then I got a low-grade fever, and I went to a doctor in Norway after, 3 days later, who actually took blood and said, yes, my monocytes are up. I had a bacterial infection, and he recommended I take penicillin. And I said, no, I think I need doxycycline, which is what you use to treat Lyme. And as you might imagine, things were tense for a few moments there. He did give in, I think rather reluctantly, gave me doxycycline, and 24 hours later it was cleared up. And then when I got back, actually I can show you a little more better timeline here. So this is when I first felt ill. This is when I was ill. This is when I was treated. When I got back, I actually had a test for Lyme, and sure enough, I was positive. I had the perfect control because I had given blood several days earlier. There was a false positive rate associated with Lyme, and I was negative then. So I had seroconverted during this time, and we could still detect some antigen as well. So the point out of all this is that actually the first clues that I was sick actually came from my wearables, my pulse ox, so my blood oxygen, and from my heart rate. And as I say, later it was my skin temperature. So that prompted us then to look at all 2 years of data where we've been doing lots of sampling on me and others, as you'll see in a minute, and just survey and see, well, how often when I was sick is my heart rate and skin temperature elevated? So this is low resolution. This is plotting per day. This is outlying heart rates, outlying skin temperature measurements. And every single day I had Lyme disease. You can't miss it. That signal is very, very strong. You'll get strong signals from that. And it turns out I had 2 viral infections I knew about. This one came later. We know it's viral. This one as well. Every single time I was sick, I had high outlying heart rates. And then there was one day here where it turns out a high outlying heart rate and skin temperature, and I didn't report being sick, but I looked back at my CRP measurements, this is C-reactive protein, and it turns out that was super elevated, same as a viral infection. So in fact, and then these are other CRP measurements today, every single day that I had evidence of a fever, in fact, I had heart rate and skin temperature, and this was picked up on my smartwatch. All right, so that prompted us to write algorithms to be able to see when you see a change in heart rate, we in fact call the algorithm change of heart, a deviation from your baseline, the earliest possible time, this is the first version has a 2-hour window, we now have a 30-minute window, where you'll have a deviation from baseline that suggests you're sick, basically. And that we believe occurs before you realize you're sick. That is to say, your heart rate starts going up before you might feel a bit groggy or somewhat. So it's a little complicated, but this is essentially a delta from the heart rate over time. And so these are my 4 times I got sick, and this is the time I would come in to visit, but this is the time when it would first show up. And it turns out we had 3 other subjects who got sick, one of whom got sick twice, and it works perfectly on them as well for the heart rate. Now the skin temperature only worked on 2 of 4 people, and for a 3rd person we know they keep their smartwatch loose, so maybe that's why that one didn't work, and the 4th person I don't know why. So anyway, the skin temperature may or may not be useful. All right. So the bottom line is we're now trying to expand this study, and we actually want to set this up in a way that we think we can tell you're getting sick before you realize it through elevated heart rate with a very low false discovery rate. The other thing I'll say, since I saw Eric looking at his watch, I must be out of time. So I'll just summarize this, that we actually can tell differences between insulin-resistant folks, which is an early form of type 2 diabetes, from basically altered heart rate and some other measurements as well relative to insulin-sensitive folks. So we think a smartwatch can be very valuable for being able to tell when people are showing early signs of type 2 diabetes. So bottom line is, over all these devices, I think you appreciate, do relay things into your smartphone, which we do envision as the command center for your health of the future. And so here's my summary. We do think omics profiling is powerful, but we think these wearables will also be equally powerful for measuring physiology. We are building personal health dashboards that actually have your microbiome data, your wearable data, all in a single place, so you can actually track these things basically over time and collect it all together to be able to better manage people's health. So these are the folks who did the work: Xiao Li, Jesse Dunn, and Dennis Salins spearheaded a lot of this, and then we'd help from lots of other wonderful collaborators as well. So thanks again for having me.